You need to watch this if you think quantum mechanics is boring. The Kochen-Specker theorem will change your mind forever. So what's the Kochen-Specker theorem? Imagine trying to label every point on a sphere with a yes or no answer, but every time you try, it just won't add up. It tells us that in the quantum world, you can't assign definite values to certain properties without contradictions. The Kochen-Specker theorem shows that our universe is far stranger and more fascinating than we ever imagined. That was in Kochen-Specker theorem in simplest explanation. Now let us dive deep into the roots of Kochen-Specker theorem. The Kochen-Specker theorem, also known as the Bell-Ks theorem, was independently proven in 1966. This no-go theorem places significant constraints on hidden variable theories that attempt to explain the predictions of quantum mechanics in a context-independent manner. The theorem demonstrates that you can't assign definite values to quantum properties without considering the context of the measurement. In classical physics, we assume that an object's properties, like position and momentum, exist whether we measure them or not. The Kochen-Specker theorem flips this assumption on its head. It tells us that in the quantum realm, properties are not intrinsic, but are instead influenced by the act of measurement itself. This phenomenon is known as contextuality. The Kochen-Specker theorem complements Bell's theorem, which established non-locality as a feature of any hidden variable theory that aligns with quantum mechanics. Together, these theorems paint a picture of a universe where certainty is an illusion, and the act of observation plays a crucial role in defining reality. After this, Kochen and Specker explore the intriguing possibility that the value attribution of quantum properties may be context-dependent. This means that observables corresponding to identical vectors in different columns of their theoretical table might not have the same values because each column represents a distinct measurement arrangement. To put it simply, in the realm of hidden variable theories, subquantum reality could be influenced by the measurement context. This context dependency implies that the relationships between quantum mechanical observables and hidden variables might only be homomorphic, not isomorphic. In other words, the connections are analogous but not identical. This revelation makes the requirement for context-independent value attribution obsolete. Consequently, the Kochen-Specker theorem only rules out non-contextual hidden variable theories, leaving the door open for contextual interpretations. The theorem also proves the impossibility of Einstein's assumption that an element of physical reality can be represented by a value of a quantum mechanical observable. This value, often depicted by the final position of the pointer on a measuring instrument, only materializes during the measurement itself. Thus, it cannot be considered an element of physical reality in the classical sense. To truly grasp the essence of elements of physical reality, we might need to turn towards subquantum or hidden variable theories. These theories propose that there are deeper layers of reality, beneath the quantum surface, that might offer a more comprehensive description of physical phenomena. In subsequent works, the Bell inequalities are examined within the framework of these hidden variable theories. Here, the hidden variable is thought to represent a subquantum property of the microscopic object, distinct from the observable value measured in quantum mechanics. This perspective allows us to contemplate the existence of multiple levels of reality, each described by different theories. Such an approach was already suggested by Louis de Broglie. For these more general theories, the Kochen-Specker theorem remains relevant only if the measurement is assumed to be faithful. This means there must be a deterministic relationship between a subquantum element of physical reality and the observable value found during measurement. But how do we bring these abstract theories into the tangible world of experiments? This is where the story gets even more fascinating. The Kochen-Specker theorem is a pivotal point in the ongoing debate on the incompleteness of quantum mechanics, a debate that gained momentum in 1935 with the famous Einstein, Podolsky, and Rosen article. This article introduced the EPR paradox, challenging the Copenhagen interpretation of quantum mechanics. The EPR paradox assumes that a quantum mechanical measurement result is determined by an element of physical reality that exists before the measurement. This assumption was controversial and not widely accepted by the physics community at the time. Niels Bohr, one of the founding fathers of quantum mechanics, responded to the EPR paradox by highlighting an ambiguity. He argued that the EPR reasoning failed to consider the contextuality of measurements, the idea that the outcome of a measurement can depend on the specific arrangement and context of the experiment. Bohr's reliance on contextuality implied a kind of non-locality, which Einstein famously referred to as spooky action at a distance. Fast forward to the 1950s and 1960s, when two significant developments emerged. David Bohm proposed a hidden variable theory that underpinned quantum mechanics, accepting the non-local nature of quantum reality. John Bell, inspired by Bohm's work, derived the Bell inequality, a groundbreaking result that could be experimentally tested. Bell's work shifted the discussion from metaphysics to physics, providing a concrete way to test the assumptions of quantum mechanics. The second line of development was the Kochen-Specker theorem itself. Unlike Bell's approach, the Kochen-Specker theorem focuses on non-contextuality, the idea that hidden variables are associated only with the quantum system being measured and not with the measurement apparatus. This theorem states that no non-contextual hidden variable model can reproduce the predictions of quantum mechanics for systems with a Hilbert space dimension of 3 or more. In 1966, Bell published a proof of the Kochen-Specker theorem, which had been submitted earlier but was delayed in publication. Since then, simpler proofs have been provided by researchers like Merman and Perez, though many of these proofs apply to higher dimensional Hilbert spaces. The first experimental test of contextuality was performed in 2000, marking a significant milestone in quantum physics. More recently, in 2022, an experimental version was achieved that closed detection, sharpness, and compatibility loopholes, providing a robust test of the theorem. As we stand at the crossroads of theoretical exploration and empirical validation, the future of the Kochen-Specker theorem gleams with promise and intrigue. What lies ahead in this uncharted territory of quantum mechanics? With the advent of quantum computing and advanced experimental techniques, the Kochen-Specker theorem is poised to play a pivotal role. Quantum computers, leveraging principles like superposition and entanglement, might soon offer new ways to test the theorem's predictions on an unprecedented scale. Where quantum processors can simulate complex quantum systems, providing insights that were once beyond our reach. Moreover, the implications of the Kochen-Specker theorem extend beyond the realm of physics. In the field of quantum cryptography, for instance, the theorem's principles could enhance security protocols, making communication channels virtually impervious to eavesdropping. This intersection of theoretical physics and practical application underscores the theorem's versatility and far-reaching impact. But perhaps the most profound aspect of the Kochen-Specker theorem is its philosophical resonance. It challenges us to rethink our notions of reality, measurement, and determinism. Are the properties of quantum systems inherent, or do they emerge only through the act of measurement?